These are some comments to help with Chapter 5, Part 2 homework. So let's just go through the problems one by one. Hopefully you've tried them before you listen to this. Problem 1, we've got a satellite in a circular orbit around Earth, and we're given the speed of the satellite. Notice it's in kilometers per second. We might want to change that to meters per second just to make things a little bit more straightforward. Determine the satellite's altitude above the surface of Earth. Assume Earth is a homogeneous sphere of 6,370 kilometers and a mass of so many kilograms. Again, I would change that to meters just to make things simpler for us. So if we want to find that radius, what we're going to do is we know the speed, so we can set capital G times the mass of the satellite times the mass of the Earth divided by the radius of the satellite's orbit. That's given down here. Again, I would change that to meters. Divided by that radius squared is equal to ma along the radial direction. That's m times v squared over r, and you're given a v. I would convert that to meters per second. M times v squared over r, and the mass of the satellite will cancel out on both sides. You've got the r of the satellite. And in that case, I believe you can solve that for r, assuming you use the given mass of the Earth there. You can solve for r after you simplify that equation and cancel out one of the factors of r. And when you solve for that r, that's the radius of the satellite's circular orbit. What you got to do is subtract off the radius of the Earth from that in order to get the satellite's altitude above the surface of the Earth. So once you've done that, you can get an answer in meters, and notice it's asking for an answer in kilometers, so then I would convert to kilometers to get the answer. Problem 2, the ratio of the gravitational force on an astronaut when he is in a space satellite of a given orbit, and this is the altitude above the Earth. So if we want the radius, of course, we've got to add on the radius of the Earth to get the radius of the circle that it's in. 2, the gravitational force on the astronaut when he is at the surface of the Earth. So the gravitational force at the surface of the Earth is just m times little g, where little g is 9.8. And the force on the astronaut when in that higher orbit in the satellite is g times the mass of the astronaut times the mass of Earth divided by the radius of the orbit squared. So if you take the ratio of that thing to mg, the m's will cancel out, and you just have to simplify it to see what that ratio is, and hopefully it's one of those answers down below. Planet Krypton has a mass of so many kilograms and such a radius. What's the acceleration of an object in free fall near the surface of Krypton? So that's really asking what little g is on the surface of Krypton. And the way we do that is we imagine dropping an object in free fall, and we do its free body diagram. The only force is the weight force, which is equal to, well, we don't need to do a free body diagram, but the only force on it is mg, so we can write it as m times little g, and that's equal to capital G times m times the mass of Krypton divided by the radius of Krypton squared. And in that case, you can solve for little g after canceling out the mass of the object and get an answer in meters per second squared. Problem 4. A geosynchronous satellite orbits a planet similar to Earth at a certain radius from the planet's center. So here they're directly giving us the radius of the circular orbit. The angular speed at this radius is the same as the rotational speed of Earth, so they appear stationary in the sky. That means the period of the satellite is 24 hours. What's the force acting on the satellite? So in this case, since we don't know the, well, I guess we have two ways to calculate. Well, we don't know the mass of the planet, so the only choice we have to get this force is to set the force equal to ma. There's only one force acting on it along the radial direction, So F equals ma radial components would say that the force on it is equal to the mass of the satellite times v squared over r. We're given r, we're given the mass of the satellite, and we're going to get v by doing the distance over time trick. The distance it goes is 2 pi r, and the time it takes is 24 hours, and I would convert that to seconds, right? 60 seconds in a minute, 60 minutes in an hour, so that's 3,600 seconds in 1 hour, and multiplied by 24, that's the number of seconds in 1 day. Problem 5, what is the mass of the planet? Okay, so now we know what m times v squared over r is. We're going to set that equal to g times the mass of the satellite times the mass of the planet divided by r squared and solve for the mass of the planet. I think we know everything else. So we'll set that equal, that gm1 m2 over r squared equal to our answer we got in part 1. Problem 6, asteroid in orbit. The period of the Earth around the Sun is 1 year, and the distance is so many kilometers. From the Sun, an asteroid in a different circular orbit around the Sun has a certain radius. What's the period of the asteroid's orbit? Here we could reason this through using Newton's second law for a circular orbit, but it's perhaps simpler to use Kepler's third law, which says that the square of the period, the ratio of the square of the period divided by the cube of the radius of a circular orbit is equal to the same constant for all things that orbit that same sun or whatever they're all orbiting. So in this case, we know the Earth's period, which is 1 year. 1 year squared divided by 150 million kilometers cubed is equal to the unknown t of the asteroid squared divided by 430 million kilometers cubed, and solve for the unknown period of the asteroid because they're both equal to the same constant, so they're equal to each other according to Kepler's third law. We don't really have to change to SI units in this case because we want the answer in years, and the units will cancel out on both sides. So if we do it just using the units that are given, we'll end up with an answer in years. Part 2, or problem 7, what is the orbital velocity of the asteroid? So in this case, if we know the period, we can use the old distance over time trick to get the velocity. The velocity, or the speed, I guess they're really asking for here, is equal to the distance it moves divided by the time it takes. And we've found that time in years, and now they're telling us, well, if we want this answer in SI units, we better convert that time we got in part 1 to seconds. So we got it in years, we multiply by 365 times 24 times 60 times 60 will give us the number of seconds in the orbit. That's going to be a huge number. And we can use in problem 7 the distance over time trick. It goes 2 pi r for the radius of that asteroid orbit divided by t in seconds. So if we put those both, again, we're going to have to convert the r to meters if we want everything to come out in SI units. Do 2 pi r divided by t for the asteroid, and that should give an answer in meters per second. Problem 8, Mimas orbiting Saturn. A moon of Saturn has an orbital radius of so many meters and a period of so many hours. Use Newton's version of Kepler's third law to find these data, to find the mass of Saturn. Newton's version of Kepler's third law is just g times the mass of the orbiting object times the mass of the thing that they're orbiting divided by r squared is equal to m times v squared over r. So in this case, we don't know v, but we do know the orbital period. So we can use the distance over time trick, 2 pi r divided by the period, and I would convert that period to seconds, to get v. And then I have g times m times the mass of Saturn. So g times the mass of Mimas times the mass of Saturn divided by the radius squared is equal to m times v mass of Mimas times v squared over r. cancel the r, cancel the mass of Mimas, and the only thing you won't know in that expression is the mass of Saturn. So solve for the mass of Saturn that way. Problem 9, orbit of Jupiter. Jupiter is 5.13 times farther than Earth from the Sun. Find Jupiter's orbital period in Earth years. This again we could solve using Newton's second law along the radial direction for the orbit of Jupiter, but instead it's easier to reason using Kepler's third law, which says t squared over r cubed for Earth is equal to t squared over r cubed for Jupiter. So in this case, for Earth, t squared is going to be 1 year squared divided by r cubed. We can just leave that as an r cubed. And then on the other side of the equal sign, we'll have that's equal to t squared over r cubed for Jupiter. So t Jupiter squared divided by the radius of Jupiter cubed, and that would be 5.13 times Earth's radius. And then we've got to cube that. And then we can cancel out the r cubes in the denominator. So we'll just have a 1 in the denominator on one side and a 5.13 cubed in the denominator of the other side. And that would allow us to solve for the period of Jupiter in units of a year. If we leave the Earth's period in units of year, then we'll get Jupiter's period in units of year. Problem 10. A planet's orbiting a star. Calculate the mass of the star using the fact that the period of the planet is so many seconds and the distance from the star is so many meters. So this is the same trick we did in class. We just set g times the mass of the planet times the mass of the star divided by the radius squared is equal to mv squared over r. And we can cancel 1 power of r in the denominators. And we can also cancel the mass of the planet. And the only thing we need to know is the speed of the planet. And again, we can use the distance over time trick because we know its radius, so we can say it goes 2 pi r in one orbital period. So 2 pi r divided by t gives us v, which we can plug in there. And the only thing we shouldn't know, I think, is the mass of the star in that case, because the mass of the planet cancels out. Problem 11, satellite near Earth's surface. A satellite is moving essentially just above the Earth's surface, so it's just outside the atmosphere, but it's still essentially at the Earth's radius from the center. And calculate the period. So here we'll just use gm, mass of the satellite times the mass of Earth divided by the radius squared is equal to m times v squared over r, and the v we will replace by 2 pi r over t, and so that 2 pi r over t is being squared on the right hand side, and then we're going to simplify that out and just solve for t, and we'll get an expression for t in terms of the radius of the Earth. And the question is, which one of these does it match up with? Probably we derived this in class, I can't remember, but you should try to do it from scratch. Io, a satellite of Jupiter, has an orbital period of so many days and a radius. From these data, determine the mass of Jupiter. So this is exactly what Galileo could have done with the data just by observing, if he could figure out exactly what the radius of Io is around Jupiter. So in this case, determine the mass of Jupiter. Again, we're going to use g times the mass of Io times the mass of Jupiter divided by r squared equals mv squared over r, and we'll replace the v in parentheses that's being squared by 2 pi r over t. And so we're given t there. I would convert to seconds. We're given t in days, but convert to seconds. We're given the r's in kilometers. I would convert to meters. Throw everything in there. The m's will cancel out for the mass of Io. The 1 factor of r will cancel out from the denominators, and you can simplify everything and determine the mass of Jupiter, much like Galileo might have done. All right, hopefully that helped, and we'll be back soon with more videos. Bye.